which I asked you, most of you will be able to solve it somehow or the other. How do you take n numbers and find for me the maximum and the second maximum number? You say sort, okay. Therefore, if you sort it, you know the exact index based on n where this will be. But doesn't sorting involve doing some operation? If it is n numbers, a typical sorting algorithm would be n square, or we can also come to log n, okay? But now you're doing something, you're first rearranging your numbers, you're preparing your set, and then you have to pick a number, right? So yeah.
When you're finding the first max, could you have it finding like both max at once, like the second max and the first max, and then like
that is one simple approach, okay, what he just said. You're reading in numbers, okay, like previously we seen this program where you're reading in numbers and you have a variable max, right? Every time you see a number, you compare it with max. If this new number is greater, we update max. That way, we'll have another variable. We'll have max and we'll have next, okay? Bear with me, this is a simple solution. Let's see the simple solution and then we will see how we can improve it if possible. So let's write max and second max. So find the max and second max of n. We did this the other day. Is equal to, let's say, the first number. The first number from the set of n numbers, I initialize that to max. And then in a for loop, I read in numbers. Okay? So this thing is familiar to you, correct? So Nathan's solution was have another variable. Okay, that's a simple solution. So I initialize this other variable also to max. So initially both of them are the same, and then we will see how we can update this program. Here, what we will do is, whenever you check for max, all you do is check for second max also. So you'll have next is equal to max, and then what if you have a case where the new number, all right, that you see in, let's say my current max is 6 and my second max at present is 4. But the new number you see in is 5, okay? So we say, is max less than the current number? No. That means we have to do another check. Now we have to check if that new number is greater than the second max, right? So we also require an else condition coming in over here. The else if next less than num okay. That's one simple approach to solving this problem, what Nathan just said, okay? Just like how you have a variable that every time sees the maximum of the current stream of input numbers, now we will also see the maximum and second maximum of the current stream of input numbers. Yes,
An issue that I can see
yeah.
is the max number is entered first.
Say that again, please.
Say the first number entered is 10, and then it just decreases from there.
Okay.
But your max and your net would be set to 10, and 9, 8, 7, 6, 5, 4, 3, 2, 1 wouldn't fall within the parameters to change next to the next highest.
Okay. Fine. So initially,
You see what I'm saying?
yeah. So you're trying to say that initially you will have a max to be and next max to be 10, and then when 9 gets inputted, okay, let me see, is that true? Max is equal to max. Oh no, that's why we have the else, right? Okay, first time max and next max are 10. Next time 9 is entered in. So we come over here. Is 9 greater than max? Max is 10. No. Else is what do you call it? Next less than equal to num? That is true. So then next will be updated in the second pass in the else condition. That's why I added the else in.
But next is less than num,
Uh,
right? Next wouldn't be less than num, but
Let's have it less than equal to then. Might be a correction then. Does that help? Less than equal to? I believe it does. In the second pass, if you have 9, now your
next would still be greater than number.
oh, should it be greater then?
Now, you would just have to not set your next to max. You'd have to set it to next equal max minus 1.
This is part of the upper if.
You did it at the top when you can play.
Up here?
Yeah.
Okay. I have to initialize it to something. I can initialize it to max. Why not?
That's what I'm
All right. Let's see the program. All right. Let's see the program, and then we'll come back to it, if you don't mind. Here.
Every time I see,
I'm not going to spend too much time on this problem here.
every time I see all those hookups for out, I keep on thinking. And wouldn't it just be simpler to just design the ports so that they would accept like VGA and stuff?
Well, I like this. What do you call this? Sublime text. And I can't install it. I'll have to call IT to do it over there. So this is a simple program. All right. I don't want to go into the working of this because, as I said, it is a simple approach. I will upload it, and you just go through it. If you run this, you will see that it gives you the maximum and the second maximum every time. Over here, initially I enter in 2 numbers. All right. I failed to mention that I enter in 2 numbers, and I have my max and min. I mean max and second max. And in this loop, I keep going from 1 to n minus 2 because prior I have entered in 2 numbers. And then I keep checking, okay? Here, I think now this clarifies what you were talking about. I had written on the board less than. Here it is max, greater than. All right?
I think the fact that you entered the 2 numbers at first fixed it because now next max isn't the same as.
Okay, then I think, is that fine right now? I think I misunderstood what your question was then.
Yeah.
All right? I don't want to run this because let's talk about the more important thing right now, okay? So, of course, I will upload that immediately. Now, what would be the runtime of this algorithm, this approach? In worst case, I am running a loop n times, okay? Let's say the number I enter in, I compare over here, okay? This is one comparison. If this fails, I compare over here, second comparison. So in worst case, this algorithm has a runtime of 2n minus 1, okay, to find the max and the min. So let us see how we can do that better, all right? When we spoke about the previous problem, I didn't really gain anything by using this tournament data structure to find the max, but I gained something from finding the min, right? Same way, let's see whether we can improve the search for the second max using a different approach. So once again, we're going to go to the tournament structure. So here I have some numbers. Let's say 8, 7, 15, 1, 6, 9, 4, and 3. So it's not going to be a surprise to you that I am going to find the max using pairwise comparison. Okay, because we learned yesterday, if I make pairwise comparisons, then I'm minimizing the number of searches for sure. So let me do that. I will compare 8 and 7, and the greater of the two will be 8. Then I will compare 15 and 1, and the greater of the two will be 15. 6 and 9, greater will be 9. And 4 and 3, okay, 4. And then on the second level, I will compare the winners. I will compare the winners. And here I have the winner. So I know what is the maximum of all. Now look and tell me, what is the second maximum number? Okay. By observing, can you find out how can I find the maximum, second maximum number?
Just have to compare the last pairwise.
The last pairwise you say, and Norson? I'm sorry, Norwood?
You could do like an if statement to find out if it's the last comparison, and then kind of another if statement within that to say whichever the second largest number set that is.
Okay. Yes, Thomas.
Mine is similar, but what I was thinking of is initialize the second max variable at the beginning, and then just for each time it goes through pairs, making this statement so that
This time we don't have that second max variable. All right, here you can consider this. All right. We know looking at this 9 is the second largest, but and you guys have been saying you should find that the second maximum is the second last or the last one of the last comparison. That's not necessarily the case. There's a property of the second largest number. Okay, we have the largest number, and the second largest number has failed in the comparison with the largest number somewhere. Okay, so let's say 15 is the largest number. What all have been compared with 15 and where? So I know that 9 has been compared with 15 in some game at least. Then 8 also has been compared in some match throughout this tournament. And 1 also has been compared with 15 or played a match with 15 at some time. So I know that the minimum has to be one of the numbers which was matched with the maximum. So if I know which is the maximum, all right, I should find out where all has any match been done with the maximum. Okay, so among those, I will then go and check which is the second maximum. All right, let us see why should we do something complicated like this, and what efficiency will it give us. All right. So I'm not going to write the text, but it'll be in the notes. Tell me something. What is a tree? What is a tree in terms of computer science and data structures?
The tree is a system of organization in a file, such as if you go into the command prompt and you type in tree, it'll bring up an entire list of directories throughout the computer.
You can think of this as a tree consisting of a node, and each node having a child node. All right. So that's the parent node. The parent node has two children nodes. This node has two children nodes. This node has two children nodes. So this is a tree. All right. You have a left node and a right node. A tree has a property called the height of the tree. Okay. How many levels are there in this tree? This is 1 level, 2 level, 3 level. Okay. The tree has a height 3. 1, 2, 3. All right. So, how many comparisons or how many contenders will be there for the second place will be directly proportional to the height of the tree. So right now we are talking about small numbers, just 8. The height of a tree, or I should say a balanced tree, balanced because each node has exactly 2 children. Each node has exactly 2 children. Each node has exactly 2 children. So the height of a balanced tree, okay, or I should say binary tree, where each parent has 2 children. It could be a tree with 3 children also. Each node could have 3 children. So this is a binary tree. So the height of a binary tree is, you can think about it as such. Let's say n is equal to 8. So 2 raised to 3 is equal to 8, right? So this is k, the height of the tree. If I have 16, let's say 16 elements, so 2 raised to 4, 2 to the 4, 4 to the 8, 8 to the 16. So the height of that tree will be 4. So we can make log 2n will be the height of a tree. So if I have 8 elements, the height of your tree will be log 2 of 8 is equal to 3. So how many comparisons will we need to make to find the second max? I know in order to find the max, how many comparisons do we have to make, irrespective of what approach you use? Let's say n minus 1, right? N minus 1 comparisons will have to be made. And to find the second max, log 2n. Log 2n means if n is equal to 8, 3. Okay, so which is much small. Let's say n is large. Okay, if n is very large, log 2 of n, you can understand how small it is, right? So let us, now we know something, okay, that in theory, if I have n numbers, I don't have to search among many numbers to find my second last. I can find my second last among log 2n, that is 3 numbers. Who was compared with the max? Who was compared with the max? Who was compared with the max? I will come to the algorithm of identifying these 3 numbers later on. But let us also understand, this is a data structures class, right? Now I need to know, how do I implement that? How do I program that? How do I save those numbers in a particular order that represent a tournament? Okay, so let us do that next. So here I will draw the same tree once again, but I'll draw it down for more space. So I have 8 and 7, 15 and 1, 6 and 9, 4 and 3, 4, 5, about what structure will you use to save this while I do this? So let me tell you that in order to first we have to build the tournament and then save the tournament. Okay. Initially we have only an array of 8 numbers. Okay. So what we are going to do is, based on the number of elements I have, I will count the size of the tournament. Okay. So if I had 8 elements, what is the size of the tournament? The size of the tournament means how many locations will I need to save this tournament. I have 8, 9, 10, 11, 12, 13, 14, 15. Okay. So there is a property. Okay. I will need 2 into n minus 1 positions to save this thing. All right. Let me number them also. There's a reason I'm going to number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. Now look. Let's look at these two, okay, as an example. 14 and 15. Okay. These two are compared, and the maximum of them is in position 7. Alright. So when I take two numbers pairwise, 14 and 15, let's do integer division of 14. What is by 2? What is 14 divided by 2? 14 divided by 2 is 7. Alright. And what about 15 divided by 2? Let's just take the integer value. Forget the remainder. 15 divided by 2 is again 7, right? So I take any two numbers and I do the integer division by 2, I get 7. So therefore, the max of these two are in 7. Let's see these two, 12 and 13. Divide 12 by 2, 6. 13 by 2, forgetting the remainder, 6. Let's take 4 and 5. If I divide these two indices by 2, I get 2, right? Similarly, 2 and 3. 2 divided by 2, 1. 3 divided by 2, 1.5, so 1. So, I know something, that the 14 and 15 elements comparison, okay, I can save that in position 7. So, in order to save this data structure, why don't I just assume I will need an array of size 2n minus 1, okay? So, let me build an array over here. Oh, I hope it'll fit. Okay, anyway. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So, now the program is starting. First thing, find out what is n. n is equal to 8. Alright? And I will have an array of size 2 into n minus 1 is equal to 15. Now it's time for me to, in the for loop, start reading in the numbers. I read the first number, okay? For simplicity, I will assume my indices start from 1 and not from 0, so we can all understand this properly. Position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So right now I'm beginning to read in my numbers. And I put my first number. Okay, I have n numbers, right? So my first number, I'm going to put it in position 8. Because I have 8 numbers, I put it in position 8. That is 8. Then I read my next number, put it in position 8 plus 1. Then I read my next number, put it in the next position. Is it clear so far? Okay. Any questions about this technique? Now, what I need to do is I need to build a tournament. So let me choose anything at random. Let me take this element 10 and 11. Okay. What did I say? The comparison of 10 and 11 go into 10 by 2 is equal to 5. So 10 and 11, 15. Okay. So you can know very well that here you should have 15. Okay. But there's a more civilized way to do that. Okay. Because we'd like to do everything in loops, continuous. So I start from the end. Okay. I know what is the end. I start from the end. What is max of 4 and 3? 4. Okay. Put that in the first empty position. Okay. Then I compare these two. 9 and 6. The max is 9. I put it over here in the next empty position. Then 13 and 1. What is 13 and 1? 13. Oh, that's over here. I already got it. Oh, this is 15, not 13. So I got that here. Then 8 and 7? 8. Okay, then take 9 and 4? 9. And then 8 and 15? 15. And then 15 and 9? 15. Alright? So, this way, in two loops, what you have done is you have built your structure. Okay? We still didn't come to the point about how I find out which is my second max. We will come to that. But now at least know that you have built your tournament in one array of size 2 and minus 1. Clear, everyone? Now over here, I have a tournament of even numbers, 8 numbers. How will it be different if I have, let's say, another element? Okay, so let us see whether we even need to bother about how I build a tree. If I needed to build a tree, then I would compare this and this. Okay, and then things would get a little messy and confusing, right? But it's easy if we follow a loop to build that. Let us see another example of an odd number. Oh, by the way, let me just highlight contenders. Alrighty. Let me say I have numbers 6, 3, 1, 9, 8. Okay, I'll take a small example. I have 1, 2, 3, 4, 5. 5 numbers. So n is equal to 5. Fine. So how many spaces or how many, what's the size of my array that I will require? 5 into 2, 10 minus 1, 9. Okay. So let me build my array. I'm not even going to bother about building the tournament. Okay. You could do something, but directly using this algorithm, we should be able to build a tournament. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 1, 2. I'm writing the index number. Did I do something wrong? Huh?
You added one index.
One extra?
Erase them.
Yeah.
Erase this thing. Okay, so now let me start to read in my numbers. Okay, I initialize my array. My first number is 6. Okay, 6 it goes in position n. So I will have 6 going over here, then 3 going over here, and then 1 here, 9 here, and 8 here. Now let me start building the second level of the tournament, right? So I'll compare 9 and 8, and I will have 9. Then I'll compare 3 and 1, and I'll have 3. Now, you remember we have odd numbers, right? So now I'm comparing the lowest level with the first level, if you notice, right? So then I will have what is this? 6 and 9, I'll have 9. And then I'll have 3 and 9. What is the max of this? 9. So that way, if you just build your array, okay, put your initial numbers in the right position, start from the end of the array, all right, compare two numbers, two numbers, two numbers, two numbers, two numbers. You don't have to bother about whether it is even or odd, all right. This technique does it for you. Now, I stressed the other day while we were trying to find the max or min that in order to do this, pairwise comparison is absolutely necessary. Okay, but think about what will happen in this situation. If I choose my elements like this, I wonder whether these are the same numbers that I'm using. I think it's the same. So I'm going to I'm not doing pairwise comparison right now. I'm just randomly doing comparisons. Okay, so I'm building a random tree. So alright, so this is some random tree, okay? It seems, which is the maximum number? 15, okay? How many matches has the best player played? How many matches has 15 played? How many comparisons does it have? Okay, let's highlight. 15 was compared over here, again here, again here, again here, because it compared there. So,
wouldn't that top one be a comparison?
oh yeah, comparison. Okay, so what is the height of this tree? Tell me. The height of the tree. Can you even tell what is the height of the tree directly? You can't tell. You can't predict what is the height of the tree because you don't know whether this is a balanced tree. Okay, so 1, 2, 3, 4, 5, 6. The height of the tree is 6. Okay, so if I don't do pairwise comparison, okay, there is no guarantee that my tree will be shortest possible. Okay, in this selection over here, because we did pairwise comparison, this tree is the shortest that it could possibly be, and the tree's height basically indicates k, the number of elements that are contenders for the second maximum, right? Here I just randomly made comparison. There is no guarantee that my tree is the shortest. Therefore, whatever is the height of this tree, that many contenders are there for the maximum position. There is 8 is a contender, 1 is a contender, 6 is, 9 is, 4 is a contender. Okay, so we have to in order to guarantee that we can find the second maximum in least number of comparisons, we have to do pairwise comparison at every level. All right. Now, I will briefly tell you the idea about how we find who are contenders for the second largest position. All right. What we do is we first find out what is max. Okay, we first find out what is max, and then let's call this I. All right, let's call this I. I mean, let's do this over here. Let's call this I, so you see what is the value of I. I compare these two, I and I plus 1. All right, we will go through the algorithm in detail, but I find the max and I find its two children. Okay, I can find its children by knowing that I have to compare if this is the max, this plus 1 and this plus 2. So I know these two, and then I will find out which is the maximum of them. Okay, this is the maximum and this is the minimum of them. So I have 9. Then I will go to the bigger of the two at that level and I will compare its two children. Okay, which is the bigger of them? This one. So I'll compare 8 and 9. All right, and then I know that 9 is one of them, of course, because it is greater than this, and because this is smaller, I will include this and then go down the tree which has the biggest number, and then I'll compare these two. Of course, this is the largest number, so I will include this. I'll go through the algorithm, all right? But for right now, what I want to do is I will upload that program that we did at the beginning of the class, that simple technique, and let us look at the tournament data structure. Okay, it's a very simple program. I will upload it, and I would like that you not learn it by heart, but learn it well enough such that if you have it in front of you, you know exactly what's happening. Okay, here in theory it's really it looks complicated, but it's so simple. Okay, so over here I have this array. I call it tournament. Okay, and you have your other variables. First of all, find out how many elements are going to be compared to find out the max and second max. N. All right, so you start to read in n numbers. Okay, where does the first number go? Yeah, we start from n. Look, we start from n, and what is the size of the array? 2n minus 1, right? So we go from n to 2n minus 1, and we start dumping elements in that index I. Everybody clear so far? Yeah? Can I move? Okay. After that, okay, go to the end of the array, the very last position and the second last position. What is the end of the array? It is 2n minus 1 minus 1, right? Because remember, I starts from 0. The size of my array is 2n minus 1. So let's say I had 15 elements. We go from 0 to 14, right? Not really 1 to 15. That's why I have 2n minus 2 over here. Is that clear why? Because in the index, we have 2n minus 1 elements, but the index starts from 0 to n minus 1. That's why. And I go all the way up to the second position. Okay, that is index 1. And every time I do this, I am decrementing by 2, right? Do you remember why? Because I compared these two, then I compare these two, then I compare these two. That's why your loop is decrementing by 2 every time. And just find out the max of position I and I plus 1. Let's say I have a function that gives me that, and I place that in index divided by 2, I divided by 2, right? Because I compared 10 and 11 and placed it in position 10 by 2, correct? So that is it. In this for loop, you have computed your maximum, and then Here you can print out the tournament to look at it. So let's quickly run this. Any questions about this? The program? Okay. Let me say I want to find the maximum of 7 elements, for instance. Let's say 5, 9, 8, 2, 5, 9, 8, 2, 6, 10, 1, 2, 3, 4, 5, 6, and 1. Alright, so I have here 5, 9, 8, 2, 6, 10, 1 in positions n, 2, 2n minus 1. And then 10 and 1 max is 10. 6 and 2 max is 6. 8 and 9, 9. 5 and 10, 10. Then 6 and 9, 9. And 9 and 10. Okay? Is it clear, everybody? Okay. Then just give me one quick second. Okay, let me ask you a question about the homework that was